Everyone to our YouTube. Sorry, I got some question or?
No, I also heard some weird noise, but I think simply go on.
All right. Maybe Stefan, if you can mute yourself, that would be great.
Hello, it's Stefan from Atos. I've just joined, and I thank you for the meeting.
Okay, could you mute yourself, please? That would be nice. Thank you. Somehow I think there came strange noises from your channel.
Yeah, of course, I'm muting now.
Okay, thank you. And again, so welcome everyone for our YouTube training race. Today we have the topic on unique AI software framework for RAISE and to enable this for Exascale performance. So it's an interesting task that we got in the Center of Excellence in RAISE to really enable us during the course of a really application co-design process to develop something we can call maybe a reference model or a software framework really of AI components that really enable scalable computing towards Exascale. And we have quite an interesting program for you today. So the agenda is as follows. I will basically point out shortly basically why we have the relevance of an AI software framework within CoE RAISE. As I said, this is largely the application co-design process I point to, but then also thinking about more larger, that of course in the community of Euro HPC and in the, let's say, maybe even international AI community and HPC community, we have the need of really understanding what AI components matter. And this goes in different ways to different modules and to different ideas of version dependencies, but we will all clarify this in, let's say, the first two talks that are given by me, just basically providing you with an overview what we actually mean with unique AI framework. So the project is half through, so obviously we don't have all the results yet. So some of that is draft plans, others is the output of the application co-design process. And when we have clarified this overview, we really want to give you a really deep down detail of one of the tutorials here, how to set up an HPC environment properly, which is one part of the AI framework that we basically provide as an output. And we have a very nice use case demonstration then coming together from Rakesh Sarma and Marcel Aach that are basically then the main part of this tutorial or training today. There should be enough room still for question and answers later on. And so let's go with the short reminder that this training is organized from different players. But yeah, before we do this, maybe shortly an introduction of the speakers. We have Rakesh Sarma as a key expert in scalable machine learning at the UD Supercomputing Center, also an expert in CFD applications, and is now one of the key implementers with us really in the framework design and underlying elements towards really HPC, using it at scale. Marcel Aach the same way. He is really now a machine deep learning expert with a specialization perhaps a little bit on ray tune and hyperparameterization, which we will also hear a little bit about, and what is also one part of the software framework again. I'm also happy to say he's a doctoral student here at the University of Iceland. That's why you see both logos. And yeah, just shortly for me, I'm teaching here at the University of Iceland high performance computing and parallel and scalable machine learning since a long time. In the frame of the Euro HPC, I'm also a joint governing board member of Iceland, which is quite interesting, and I'm happy to be in RAISE and see a little bit here also this kind of training co-organized from our National Competence Center for HPC and Simulation and Data Labs that we have under the umbrella of the EuroCC project, and of course soon hopefully the EuroCC2 project. So there on ehpc.is you will see basically several communities with simulation and data labs created in different areas of science that use HPC in one way or another. So many people here, like the remote sensing lab, are contributing within CoE RAISE with their expertise, and of course also in the CFD lab and others. So the strategic element Exascale is of course quite an interesting word, but now we see from the government board perspective, we implemented this. As many of you know, we will have in Juli, hopefully in 2023, 2024 now an Exascale machine. It's confirmed by the governing board. The call was closed and the application got basically approved. Of course, obviously the UD Supercomputing Center needs to develop this now in the next 2 years to really get it up to scale. New building, new infrastructure, an exascale machine to build that, of course, requires some new pulling of strings. And without saying, of course, we have certain challenges of energy here in basically in the Jülich Supercomputing Center in Germany, but still collaborate a lot also with Iceland on that, and also with Luby in Finland, that are all following basically a so-called modular supercomputing approach. So that's how we basically work together and how this RAISE project then chimes in when we talk about Exascale. Now let's come a little bit to the idea of basically why we need such a RE software framework in CoE RAISE. What was the idea? What is basically coming out of RAISE and how we tackle this is basically now the idea of this talk a little bit. Of course, RAISE has much more to offer. We do and implement AI models in different use cases. So if you want to know more, please go to the RAISE website to get more information about CoE RAISE. The framework is just one approach. And the overall approach is usually that we try to really make a comprehensive view on doing simulations and experiments combined with AI technologies. And this in a way of doing it towards Exascale. So really thinking about surrogate modeling, how we deal with big data coming out of the simulations, learning from them to really also augment simulation design, which is a bit the unique selling property that we have here in the RAISE project. But you have also some data intensive use cases, which are not directly simulation sciences, but which are also raising cutting edge requirements towards Exascale and computing. So we have this different types of use cases, as I was alluding to. There's this kind of compute driven use cases, 5 of them in different areas of sciences, from turbulent flow over reactive flows and engine design. And then basically the data-driven use cases are basically fundamental physics from CERN, for example, but also manufacturers of large 3D printers or sound engineering, creating ears for better hearing in the future. So basically these use cases are used then for co-design our framework. And now when you look into them and dive into them, what we do in the CoE RAISE project, you will find that all of them have obviously very different skill sets in their different domain, right? So it's clear that here for AI for turbulent layers, for instance, what we'll hear a little bit later also, has lots of CFD modeling, a skill set around using these numerical methods, but also requires then lots of tool sets, which are quite established for the simulation sciences, using different tool sets. Let's say OpenFOAM for CFD is an established tool, for instance. But when it comes to AI modeling, what we do now here in RAISE, you see that also here, different tool sets are always required. And this is something where all of these different sciences may or may not be so familiar, especially when it comes to the porting of those into different HPC systems. So there's a wild jungle, so to speak, when you create all your models and your data sets, and alongside the models, in what type of technologies you want to actually deploy, in what technologies like PyTorch, TensorFlow, you want to create cutting-edge deep learning models. Which of those scale? Which of them are not scaling? So these are all questions where the RAISE project chimes in, and also then thinking about that these tool sets should run in one form or another, also on cutting-edge HPC machines, such as those that we have today, but also, of course, the Exascale machine in Jülich, and also, of course, the Euro HPC systems that we have around Europe these days. So this is quite a challenging task, and I will basically give you some insights later why it is so challenging. Just a little bit for the HPC and the idea of crossing that with AI modeling here in the work, in the idea of how basically RAISE is organized. You see that we have really an integrated way of having the use cases always alongside so-called cross-sectional AI methods, which is our work package 2, crossing work package 4 and work package 3, so that we don't have separate solutions, so that we rather try really to build something together and create, let's say, new offs for people that are maybe not so deeply in AI on work package 2 perspective. On the other hand, we just don't do always, let's say, some benchmarks. We also concentrate here and there on the real impact in science scenarios. And this could be many techniques. We have new models that we introduce. We have neural architecture search or hyperparameter tuning, which in one way or another, almost all applications of AI could take advantage from. And we will hear more about this later on. So the overall idea then of RAISE, and this brings us a little bit already to the unique AI framework, is then to use basically what we have in hardware infrastructures today without losing sight of tomorrow with graph core or quantum annealers, quantum computing, and of course all the software infrastructures we have, right, from PyTorch, TensorFlow, Horovod for scaling, maybe even DeepSpeed for scaling. We also analyze this. And then basically use these software and hardware infrastructures and to work with our computing-driven and data-driven use cases that I'm already alluding to. And the idea is to basically create something we can say is a unique AI framework that is a little bit more generalized, but where we can make a stamp on and say it's RAISE certified to scale, right? So these are the components. If you use that, we basically did benchmarking. We used it in different applications that are maybe similar to yours. That's basically what we can recommend if you want to do AI on scale on HPC today. Obviously, we base on good foundations with open source software. We don't want to recreate the wheel. So we base our solution on TensorFlow, etc., but also on the lessons learned from EuroHPC and RAISE in the past, of course, and also work together with our EuroCC National Competence Center. So basically here, the idea how we did this now, to think about really having a methodology between the different, let's say, AI experts and then all the use case experts. We had different techniques where the fact sheets technique was basically the first we started on, was basically created in order to have, let's say, an overall overview, identify certain components that may be relevant for the components of the unique AI framework we see later, and then really having it as a living document and understanding each other. And it's experience that flow into this from many other EU projects, basically in this regard. And hence, also, if you're interested to use them, you can basically also contact us and you have availability of the fact sheets, just basically get in contact to us. Then the next idea was really doing interaction rooms, which we basically have then a much more interactive way between the use cases to really think about what are the codes, libraries now in detail, what are the contacts, but also what is the HPC system usage in the moment, or where do you want to go to? Are you using EuroHPC machines? Do you do EuroHPC regular calls right now? Which are the platforms you want to go? So of course, this goes alongside, which is one of the key elements here in RAISE as well, machine and deep learning approaches that we discuss. And of course, if you want to hear more on that, you will see here the interaction room YouTube link. Of course, you have our YouTube channel as an advertiser. And if you like us, please subscribe us. We would love to see that. We basically came out of this with some obviously components for the AI framework, but also with a large, let's say, cross HPC AI methods table that you see here. And this is something where you see we constantly improve that. So many of the previous trainings already have shown this basically interesting table. And you see it now that it basically comes more and more, let's say, elaborate. And we see also that several use cases inspire each other by saying, for instance, autoencoders just was starting a little bit here and then going more and more broad now to other use cases, since there are details and there are good examples where others can build on. And of course, we communicate alongside in both directions in work package 2 with the use cases in work package 3 and 4. And then with this table, we monitor, so to speak, and provide trainings along the way. As you'd remember, we had one of the YouTube trainings on autoencoders, of course. We also see the move to new models. Transformer models are quite interesting right now, where several use cases now start to engage in. And this is something where, of course, RAISE also has to provide a framework that works with all of these interesting components we just saw. Now, this is the RAISE Unique AI Framework as a general overview, and I have another talk now where we go a bit more details of the justification of that. That's why I basically would say here, this is the result, but of course, you want to know a little bit today how we come to all of these results, to all of these building blocks that you see here. So this is the motivation, so to speak, for the third talk of me, where I then going to basically give you some insights, how we come to the requirements that you have seen in this picture. All right, So, and this will be now a little bit more giving you a real overview about the unique AI framework, which requirements we really gathered, what processes in place in the RAISE project to do basically updates of those requirements. Many of you will know AI is a very lively field, new components coming, and then of course you want to know how to basically then also update the framework if needed. So this is something which I will shed light in now. As I said earlier, this will be just an overview, a real deep down example of one of its facets, so to speak, will be given then from Rakesh and Marcel afterwards, so that you get a more deep down feeling where we can make a difference for researchers. And let me start a little bit again by connecting to what I said earlier. We really, with the framework, have in mind to support these 4 channels that, so to speak, get into the unique AI framework. So we have this hardware infrastructures that are constantly changes. And basically also as a PI, you always have grants or computational grants on, let's say, 3 or 4 of these different machines. Not forgetting that porting your application to a new, let's say, disruptive computing model, like unique, for instance, with a quantum annealer, may be also different. And there's constantly hardware improving, like we have now interesting graph core chips that basically implement the kind of CPU that is really tailored for graph computing, which relevance for us as well. So all of this is what we benchmark, what we analyze. We have the already established results, basically that we have in a GitHub repository that can make available. And then, of course, the same goes a little bit for the software infrastructure. Many things change quickly. Many of you know TensorFlow 1 to TensorFlow 2. This shift has caused lots of trouble in the community because there are many models on TensorFlow 1 which couldn't be so easily directly ported into TensorFlow 2. Or if you just want to do and drop an Onyx and kind of open neural network exchange format standard and then load it into another model, this might cause changes when you basically want to then have just another AI framework implemented. And this is something where some optimizers may not be available or not. And these are things we also look into it. How about the portability of using Onyx between the different machines and so forth? So then, of course, the computing-driven use cases, data-driven use cases, as I said earlier, build our foundation of the inputs and requirements that I will report here. But many of us have PhD research groups. Many of us will have basically different people already with, consulted with many different experience over the years in different partners we have, like Barcelona, Jülich, or all the partners in the project that basically have, let's say, really large HPC systems and know a little bit about what's happening in these machines. So we would say this is the initial idea how we can create this framework, but we make sure that also outside this closed community of RAISE, so to speak, to make it more an open community, also relevant for others. And that's where the unique AI framework comes in. The idea is to expose that to the community, saying based on our experience with these frameworks and the data-driven use cases and compute-driven use cases, that's what we recommend to all the different community members adopting AI and HPC. Now, I said also already on this slide, this is easier than done. When you go to all the different, let's say, 9 use cases here, which is already a quite interesting fraction of our traditional HPC users and our more recent new data-intensive users of HPC, there's a massive variety in all of the tool sets used, in the skill sets that are existing in AI, the modeling versus, of course, also the knowledge, what is possible with what technologies. So in this sense, it sounds so easy here, but take away the message that it's not only adopting a logo here, right? It's not only adopting a HPC, picture here. These systems change a lot. They have extreme details that we basically neglect by having a small picture here. Do you want to jewels, partition A or B? Do you want a booster module? Do you want to do the basically cluster model? So all of this is different areas. Very low. Then speaking, you have different modules. We will come to that as well. And then, of course, you may be interested in porting. So you have not just one machine. You want to have this on 3 or 4 machines, where another challenge comes in. Equally with TensorFlow, PyTorch, different versions, they require underlying libraries in specific versions and different modules to be loaded on all the supercomputers, where Marcel and Rakesh then will also show you some good examples and details of this. So it's a quite complex task. And as I said, the fact sheets are available for each use case. Just let us know what we have done there, which gave rise a little bit to the components in question that we then analyzed in the CoE RAISE project. And we then performed really the interaction rooms and came out really with the first set of approved components from all the 9 use cases that say, yeah, that sounds right. And of course, it's an open process. So this is something where we constantly have still interaction rooms with all the different teams. We have something new maybe found, like transformer models in one use case and inspires others right now. But of course, this has now some interesting kind of history that we were going through. And just to show you some examples, what the requirements gathering process actually found was, of course, the challenges of all these developers working with a lot of different versions of TensorFlow. You see here some examples just listed as a small indicator that the technologies itself in the AI domain rapidly evolve. And you have different versions of TensorFlow that work actually with different modules already in the HPC system and need to be in different specific versions, maybe based on Python. So here we had seen differences, for instance, moving from 3.8 Python X, whatever, to 3.9. It causes huge of differences in the module loads, in basically things that really worked again as it was before. And maybe it was just 1 week ago when you tried this just because it was a new Python version. So here we saw the same challenge. This is obviously not only bound to TensorFlow. So here we saw different challenges everywhere along the line of all the AI frameworks, with PyTorch, Horowat for scaling, Raytune as a hyperparameter optimizer. So we have, of course, all the sets of AI models, which are always there in different versions. And I think just by changing one Python version, maybe, basically you have messed up all the different modules. And this means time to be invested, right? Which we should always keep in mind. So if you retry and nobody gives you really recommendations, what is now the right TensorFlow version to use? So, and for instance, also how it works with YouTube code together, with maybe before was on TensorFlow 1. So that's something where you have to see where RAISE tries to analyze these requirements and how we can address them later with the framework. Another area which is probably quite known is if you have a job script on, let's say, Jureka in Jülich and a job script on Jubels on, basically there you have different modules to load. When you go then off to Jülich, to Barcelona and to Iceland or wherever, of course, all different versions, again, in modules. There's not a common way how to do this. So basically, if you want to have then a kind of an example, usually the idea we found is there's a PhD group or a kind of research group, and they exchange via emails, hey, that is my job script that was just running last week. So please try that and modify it to your own needs on the data, right? Because everything which on the websites and so on is a little bit outdated, or but the real way how it works together is not really there. And that's something what we found is really where we can make a difference to systematically check these modules, are they still running, and have, let's say, these modules prepared in GitHub structures in CoE RAISE to say, this is an approved way how we just tested it and it works, to avoid always this email back and forth with, let's say, this job scripts and other ideas. So of course, this is just one facet of the framework requirements we try to address here. There are others on a more higher level. When you think about Jupyter, Jupyter is a very nice high-level way to access the systems, but here and there you need specific kernels of Jupyter notebooks to link them to the right modules, again, to the right NVIDIA drivers. And also there we found throughout the use cases, there's really an unstable environment. The same Jupyter notebook, which seems so obvious to many AI researchers, you load now and you load maybe in a month, is not working anymore because the kernel somehow has now to load new, basically, elements in the HPC domain, because it has to fit. It's a high-level Jupyter GUI that you use, which is very convenient, but it has to match the lower-level HPC modules available when you compute on a specific machine. And this is also an idea where we found there could be a kind of an added value from the RAISE framework to think about that all of these time investments that PhD students, PIs do right now, which is in the time scale of hours or days really per month, to really basically provide them the infrastructure they need as part of the software framework, and basically a tested one. So this brings me to the time effort challenges when you go throughout the line. And I think Marcel and Rakesh will basically also put a little bit of context to this, when you have concrete modules and concrete ideas, how basically lots of time is lost when people jump on a new machine, they want to do and identify the right modules. And the same is true for Jupyter with the kernels. And then, of course, many of the other people also said the selected debug tools, solution tools were not known. So sometimes things like NVIDIA SME, where you see, okay, is my GPU really used or not, is also not used to many AI developers that are used to develop AI, but not really are towards scalable computing right now. So in the sense, we provide there also in the framework some previous configuration that works. And this is also one part of the framework, if you will. So summarizing this a little bit as initial results, of course, we had this requirements 1 to 9, where we know, okay, this is something now what we have learned, different HPC systems, we need the underlying packages and versions of all these deep learning technologies that are there, and it's on the hardware and software level. What we don't know is really when we talk about Exascale, how they actually scale. There are lots of these different technologies that enable distributed scaling at scale. Let's say Tarantella, there's Heat, there's Horowat, PyTorch, GDP. So what we found out, for instance, we look at these technologies, we benchmark them in our RAISE environments that we have, and when we there basically have seen its good scaling capability, where we can at least say, well, that's towards Exascale, because nobody has an Exascale machine here right now in Europe. So of course, this is where we need basically the next period of RAISE to check that really. But this is something where Horowat and PyTorch DDP maybe give good scaling, and then we can say this is a RAISE approved, or let's say RAISE certified component. Here, please go ahead and use it. Then, of course, we think about bridging to the larger AI community. So think about ONNX models, right? If you have things like OpenML or other people in the AI community that not previously used our machines, they maybe just want to drop an ONNX and want to load an ONNX and basically then work with our technology. So we have to be interoperable with the standards, and that's what we also do. We're checking this with the inference background that ONNX has, but also in a way, how realistic is it to drop an ONNX, let's say in PyTorch, and reload it in TensorFlow again. So these are things we're looking in, and you see the framework has now different facets. So some are clear components where, okay, TensorFlow together with Horowat maybe scales very nice, or PyTorch with CDP scales very nice. Others really are on a different interface level where you say, is it really useful to work with ONNX models or not? And this goes on. If you think about the usability in the AI domain, many people like Jupyter notebooks and Jupyter lab environments. Of course, there we support this. And this means you don't want to go and lose the time in creating your kernels for all the different models, for all the different machines. Not only within RAISE, if you see about the EuroHPC ecosystem, where many different EuroHPC systems will become online and are already online for computing calls, and in the future, really need to have a, let's say, set of kernels that are already existing to the right set of modules. That's something what we address and want to implement in the future. Still not losing sight of low-level access of batch submission, but where we can maybe do some automation, where we think about something like a job script creator, where the modules that you really need, if you just pick Jewels and TensorFlow and Horowat, maybe from a checklist, you get automatically the modules basically that are required for this and that are proven to be worked on this particular combination of the system. Obviously, that means the rest of the script needs to be still tuned to your data and basically to your application itself. But still, you have not the pain to really analyze the real module versions. Do they really work with this particular TensorFlow on this particular HPC system? So this is, of course, still something we want to support. And thinking about reproducibility and open source and bridging to other communities, MLflow, ClearML, things we also did trainings on before. So basically the ML ops community, which has some ops, especially in business and industry, is of course by tracking all the AI models, something we also look into it. And this also here and there means a little bit about containerization of this, which brings me directly to the next topic. You see here, enable support for container technologies. Now you still see a singularity. This has been switched a little bit to Aptainer, but still basically the idea is to work a little bit, especially with industry partners that are quite, let's say, active in this domain of using containerization more and more And the AI community also uses this actually. And so this means how can we basically establish their interoperability in order to make the software, let's say, accessible to more people outside RAISE that maybe previously don't really have used HPC before. And this means also to the OpenML community where we had specific trainings on, right, for instance. So then, of course, from the hardware perspective, now thinking about more that another challenge will kick in terms of accelerators, or maybe also of disruptive technologies coming from the quantum domain. You know, many of the applications right now use NVIDIA GPUs, for instance, and we will see soon AMD instance, for instance, in the Lumi HPC or Lumi Euro HPC system. So there we will see much more heterogeneity of hardware in the future, where we also provide some components where hopefully our framework can actually scale beyond that and basically be abstract from that and enabling still, let's say, the right set of modules to make basically, even for users, the experience that it makes no difference if it's now AMD or NVIDIA GPUs. Obviously, the performance may differ, but let's say you don't have to know the deep down details of which libraries you have now to do instead of NVIDIA for the AMD accelerators. And then think about data a little bit. Of course, working with large data sets is something we expect in Exascale as well. So looking at I/O capabilities, also looking a little bit what Admire is doing in the Euro HPC domain and AI, I/O, and so on. And basically looking into this is also part of the framework. So how we can guarantee there's some certain proven methods, how we exchange big data, how we work with big data, in the use cases that may even refer here and there to parallel I/O, but also to go beyond this with data transfer. So lots of these requirements, and now your question is, okay, these are lots of requirements and this will evolve over time, surely, and that is true. So that's why we have the interaction rules where we go towards a co-design input again and again, let's say an iterative circle with all the use cases together. We had our first framework. What you just saw is basically already our second framework, where soon there will be also some news of describing that on our website. And for just an example how that basically could work is that you see a little bit here that in the requirements by discussing that some use case certainly then was establishing with us an idea of using the hyperparameter tuner, RayTune, was actually getting more and more good results of doing so, and also for scaling up on our machines very nicely. So we implemented in the framework, and with this we also had this as an input to many of the other, let's say, tasks, and the idea of basically working together with other work packages then and saying, when we have this framework realized with all its component and unique AI framework components, we of course have another round and influence other work package 3 and work package 4 use cases, right? So with this, it gets distributed. So more and more people now have heard, okay, hyperparameter RayTune, that seems to be a good model. Others have maybe used Optuna, but now gradually also moving to hyperparameter tuning, where we in RAISE have extremely good results across all the different use cases. And this is one example of this framework creation can be. So we can now by heart say, actually for RAISE use cases, at least RayTune was the best option we could switch right now to enable scalable hyperparameter optimization, which for sure has Exascale relevance, because with different configurations of your parameters, you can easily fit an Exascale machine of deep learning models when you think about also neural architecture search, which is very aligned. What architecture, what are your hyperparameters, learning rates, and so on. It's a huge search space to find the optimal model. And of course, this is one important part of it. Needless to say, we did some hyperparameter tuning seminars, but we will carry on also like we do today to also teach more about the basically building blocks of the framework that we have right now. So basically there will be more and more details also like we see in the second part today from Marcel and Rakesh, where we really dive into what it does mean to have these components of RAISE used, how is the job script generator actually used. These are all things which come now in the second half of essentially the framework realization, the second half here of our RAISE project. So I still encourage you to go to our YouTube trainings. They also here and there have, even on the methods level, YouTube training, not only distributed deep learning or so, but also how end-to-end coders are used, or the facets I said with ML ops, for instance. These are all different ideas how to do AI, so to speak, which all relevance in CoE RAISE. So this is a process how we keep it up to date. And I mean, now basically it's the time to see the framework all in all. And you see it here, as I said earlier, the requirements really shape the design coming out of the CoE use cases. So when you take here a checkbox on these couple of requirements, we see that we have to have some Jupyter notebooks really available for the community here. But the point is that they have to be, work with specific versions of modules in the specific HPC context. And that means we have to provide those which are run on, let's say, jewels, which are run on BSC or RTU or universal license systems, prototypes. So there's a direct linkage, right, where we provide components that are then, working really on all these different systems. Our vision in the future is, of course, that Jupyter might be available on more and more Euro HPC machines in the future. So Catalina and so on to Lumi. So in this sense, we also will work with RAISE to make it available for all the different Euro HPC systems in cooperation with the national competence centers and for the Euro HPC hosting sites, of course. So another requirement that we have seen was really then that some people in the communities here and there don't really know how to use HPC. They've been using workstations, a couple of GPUs, and to really have something which is much more easier, maybe for scientists to adopt this, might be instead of diving into all the modules, losing a lot of time. And even for those that have already established basically idea how to use an HPC system, also they use lots of time of analyzing what is the ML you really have to load, in which version, on which system, especially if you port between 5 different HPC systems or so. And this is, of course, necessary because you have different calls in the future from the HPC community. You will be basically getting time on different machines throughout Europe. And there we also have to make sure that the same set of framework and the same set of idea works. So here the idea is, can we do this kind of job scripter functionality, where I said you basically just say, I want to be on Lumi, I want to be on Jewels, I want to be on Mare Nostrum. And okay, what do you want to do there? I want to do TensorFlow. In the end, I don't really care about the low-level detail, but at least give me the modules that I need to load. And this could be, of course, also Python API. Alongside this goes, of course, the idea of not only having the right versions for all these different modules, and then the scaling with Horowat and PyTorch GDG or so, created then as kind of small snippets that you can use in your code. Also the Onyx idea of them really linking to existing tools from the, let's say, MLOps idea, but also when you think about the OpenML community, where we had also trainings on, they have an established set of community, not really working a lot with HPC. Can we do something to make them easy port on HPC systems, basically? And with this, it means new users for the Euro HPC community here, which I think is also very much important and which we can really provide is the scaling. So this is another aspect of the framework design, which ticks then the boxes of different areas, which we basically have seen also on a slightly different level than the Jupyter notebook. But when you go to a lower level, of course, here the Python API that abstracts from this low-level packages are going alongside with this framework API that you have there, where you basically have then something what we would say a repository available of lots of different, kind of ideas how to use the different systems with proven job scripts, with proven ideas how to use the HPC systems with different versions of the different technologies already available. And then the API or the job script functionality can easily then leverage this and basically give the users then the right module to load right now. We don't see it completely automized. It is semi-automized because obviously users have their own data. They have their own, let's say, models they want to use, autoencoders or sequence models with LSTMs. But at least they know the module set, the versions, and have a certain guarantee that this is really working, basically, and this gives us to the idea of this RAISE certified. Finally, which was also a little bit new alongside then the hyperparameter tuning here, was the idea of using Octane and container environments more, because we also want to build up collaboration with industry, which are much more usually used using container environments. Like I said earlier, with Singularity, now the move to Octane. So these are all the requirements and the idea of the RAISE Unique AI framework, and we will have now coming up trainings in more and more detail. I leave it here for this idea because Marcel and Rakesh will pick on one of the facets with different modules now as part of the training, just to let you know where our vision is, our impact in the future, where we want to go with this framework. So obviously we have not only the framework, we have also certain skills alongside it. So here we're really thinking about addressing the European researchers and scientific community needs, working together with digital twins, domain-specific COEs, and so on. And then having basically consulting and trainings done that we basically do together with them to improve the AI modeling at scale. Then on the other hand, you have also, of course, all the EuroHPC sites and the national competence centers existing in Europe, which is one channel, so to speak, how we want to enlarge our co-design, seek new cooperation partners, where we think of something like you see here, RAISE certified. So that means we have a proven set of components. We will work with basically these hosting sites together, and will then give them a certain credibility to say, well, that really works at scale. We have analyzed it, we have all the benchmarks, so that should work. And with this, basically a hosting site can get this RAISE certified logo, so to speak, and with this have hopefully much more impact with the RAISE framework than we have now in the RAISE project. Of course, here we have different impacts to, of course, the EuroHPC users, end users, but also admins that maybe save a lot of time when they adopt the RAISE framework rather than doing all their benchmarks on their own that we already have done on many different platforms, actually. On the other hand, of course, that this should be not neglected. We have our industry track where the partnerships with EuroCC and CCs again come into play, especially in their wide variety of the industry tasks. And here we also foresee doing industrial experts consulting and training, how you really use HPC at scale, or basically porting from a small workstation solution maybe to a real distributed deep learning solution. And here we address and try to address European business communities, SMEs and others, potentially also thinking about working with other partners in the future. One of it I have here said already, which is a little bit orthogonal through all of this. You see this blue line here, and mentioning again the OpenML community, which is quite established and quite interesting. And there are many others, and potentially for us of relevance would be probably also the European Digital Innovation Hubs coming up in Europe in the future. So that's all I leave on the table here for you. Obviously, it was just an overview of the framework, and we will hear now much more details from two of my colleagues, which are really experts down on the level of the machines. And it's my pleasure to have Marcel and Rakesh, showing you some more details of this framework.
Thank you, Morris. So you should be able to see that.
Yes.
Yeah, works. Thanks.
Okay. So yeah, thank you, Morris, for giving a general introduction to the unique AI framework. On a more concrete level, Rakesh and me will now be talking about the frameworks that, or the external frameworks that are part of this unique AI framework. And we try to really show you with some basic Python code and some basic start scripts how to use these frameworks on our systems. The problem you maybe already had when you've been active in this project is that there are lots of different frameworks available. The three most common ones that I will focus on here in my task is PyTorch, DDP, Horovod, and DeepSpeed. And in all cases, I will only focus on the data parallel functionality of those frameworks, although DeepSpeed also is very well suited to be used for model parallelism. And apart from these three frameworks, you also have lots of different HPC machines available. Just here in Jülich, we have the Jewels Booster machine. We have the Eureka DC GPU partition with over 100 NVIDIA AI 100 GPUs. We have our prototype system, the deepest machine. But for example, in Barcelona, there's also a AMD machine with AMD GPUs available already. And the main problem now is that you have these different frameworks and you have these different machines. So that usually means in order to use these frameworks. You also need to set up your code in different ways. You need to load different modules to run the frameworks on these machines. And I will now show you a bit how to set up an environment on these HPC machines to run your distributed deep learning training. And after me, Rakesh will give an introduction, also showing some code to how one of these frameworks is actually used in one work package of the RAISE project. We already have a very large JIT repository available where we put lots of example scripts. Currently, the full repository is only available for RAISE members, but we have a public version in preparation, and some code and a very extensive documentation for that code is already available for everybody to take a look at. The GitLab repository covers all these main machine learning frameworks and all these main HPC machines. So when you take a look at the screenshot, we see the AMD machine in Barcelona, we have the Deep machine in Jülich, and of course also the Eureka and Jewels machines here in Jülich. We try to keep it up to date and also add new frameworks. For example, you also see there's Heat, or we also have an example already how to run things on these new GraphCore accelerators. But of course, as things update on like fast, it might not always be up to date. So it could, of course, also be that some of the code you find in this repository is not up to date. To get some information about which framework has the best performance, I would recommend you take a look at our earlier seminar, which we had last year, where we also showed some scaling plots on the actual performance. And we did some comparison between the frameworks and took a look at how they actually do on our HPC machines. So let's dive in. I will start by showing how to use Horovod on HPC machines. And in general, we have two kinds of scripts you need to run things. The first one is the actual Python script. This script contains the code you write. So you define your module, you build the optimizer, you do the training and everything. And this Python code is usually independent of your HPC machine. So in most cases, you can actually use the same Python file on every HPC machine. The thing that is different from machine to machine are the so-called Slurm script or start scripts. And they are used to set up the right environment, to set machine-specific flags, and then to actually launch your Python application on the cluster. So let's start with the Python script for Horovod. At first, you of course need to do the initialization, and for that you need to import the specific Horovod library that is built for. In my case, I'm using Torch, so you need to import the Horovod version that belongs to PyTorch. Then you just call Horovod init, very simple. And then you need to make sure that the so in my case, I'm just distributing the learning across GPUs, but of course you could also probably distribute it across any other type of accelerator. But in our case, we need to pin each GPU to a local Horovod rank to make sure that all things work correctly. As a next step, we then define the dataset and data loader. In my case, I'm just using the very basic Cypher 10 dataset. Then you need to define the train sampler. And there's actually, from the Torch backend, there's a distributed sampler available. And for this, you need to specify how many how many samplers you want in total, which is the number of replicas. So we set that to the total number of GPUs we have. And then you need a unique identifier for each train sampler, which is specified with the rank. And so the Horvath rank command also returns the global rank of every of the GPU you're currently working on. And once you have defined your train sampler, you can define the train loader. And the thing you have to pay attention to here is that when you set the batch size in this distributed fashion, the batch size always refers to the local batch size per GPU. So that means if we have, for example, 4 GPUs here and we set a batch size of 1000, that would mean our total batch size would be already at 4000. Then as the next step, we can build the neural network. Again, I'm using a very simple, just ResNet 18, which I then need to load to the GPU. Then we can define the optimizer. Here I'm just using a very simple stochastic gradient descent. And the important thing you need to pay attention to in distributed deep learning is that you need to scale your learning rate with the number of workers or with the number of GPUs you are using. And the reason for that is because, as I've showed you earlier, you also usually scale your batch size with the number of workers you're using. So larger batch size usually means less optimizer updates. So in order to still get good results at the end or comparable results to when just training on one GPU in terms of the accuracy, we need to make larger optimization steps. So scaling the learning rate just with the number of workers is a very good way to achieve like a baseline performance. Of course, there are lots of other things you can do to tune that value as well. Then specific for Horvath, we call this distributed optimizer command. And then we just need to broadcast the current state of the model, which is in our case, just the initial state to our processes. We define the loss, and then we can already start our training function. So this is, quite simple. I assume you all know how to do this. The only thing that may be specific to this distributed deep learning here is that you need to, of course, move the data you get from your train loader to your GPUs. Then you perform the training procedure just as you would do when you're running things on one worker. And the thing that is important to do after an epoch, for example, when you want to know how well your model training has performed, is that you need to reduce your loss. And or reduce in this case means that it will collect the current loss from each of your GPUs and average those results. And of course, you only want to print that out once. So when we print things out, we need to make sure to just print them out on the main rank, which corresponds to the rank where Horvath is 0, where to the 0 rank of Horvath. That's about the Python script. So just a very simple ResNet 18 trained on the Cypher data set. Now I want to show you how to build your Slurm script, for example, to run this training on Eureka. And the first commands you have to set in the Slurm script are the job name, of course. Then you have to specify the account where you where the compute time you take to run your training gets deducted from. We can set an output and error file where then the results will be printed to. And of course, you also need to provide an estimate of how much compute time you need. Then in the next part, you need to specify on which partition of the system you want to run your thing. Because I'm on Eureka, I chose to run it on the DC GPU partition. And then you can specify the number of nodes. And this is important for Horovod. The number of tasks per node, in this case, needs to be equal to the number of GPUs per node. And as we are having 4 GPUs per node on Eureka, we set the number of tasks per node also to 4. And the number of CPUs, I usually set to 32, which is because we have 128 physical CPU cores on Eureka. So with 4 tasks per node, that means 32 CPUs per task. But setting it to that number is not, you don't have to do that. You can basically choose any number you want, though it should be reasonably small. Then the important part is to load the right modules. So you have the right libraries available. And on the Eureka machine, you first have to specify which production stage you want to load your modules from. Then you need to load the GCC compiler. I then import OpenMPI and the Nickel framework, which is the communication backend from NVIDIA, and is therefore well suited to be used on NVIDIA GPUs. Of course, I need a Python version, and then I also import PyTorch and Torch Vision and Horovod. So in my case, I have actually all the modules I want to use available, already installed on the HPC machine. So if I just want to run my basic training script, I actually don't need my custom environment anymore. But in case you have more modules which you cannot find on already pre-installed on the HPC system, you can always create your own custom environment with pip or conda, for example, and install those libraries into that environment. And they are also in the GitLab repository I mentioned in the beginning. There are also lots of example environment generation scripts available. Then you need to make sure that all the CUDA devices, so all your GPUs, are visible to the program, which we do with this command. And then in the end, you just run your Python script with this srun command. And that's basically already everything you need to know to run Horovod on Eureka. I also have some slides prepared to show you how to do it on Deep. And here I highlight the differences. So in my case, also the compute account on Deep is different. So I need to specify that. The partition name on Deep is also different. This is the Deep ESB booster. And here I have just 1 GPU per node. So I also set the number of tasks per node to 1. In terms of modules, we see that, yeah, this looks similar to the modules I load on the Eureka machine. Again, OpenMPI, the Nickel backend, Python, of course, but currently, at least the newest PyTorch version is not available on Deep. So if I want to use that version, I need to load my custom environment where I have installed PyTorch into. And the same is, of course, true also for Horovod, which is not pre-installed on, at least on the newest version, not on the deepest machine. Then again, I set the visible devices to make sure the program can see the GPU, which is on the deep machine, just 1 GPU. Okay, that was Horovod. So let's move on to the next framework, which is the PyTorch DDP framework. The initialization looks a bit different here. So we, instead of Horovod, we are importing the distributed backend of PyTorch. We first run the initialization command, and here we have to specify which communication backend we want to use. And because we're on NVIDIA GPUs, it makes sense to use the Nickel backend. As I said, it's the one that's programmed by NVIDIA. And then as a next step, because we are using these parameters, these assign rank parameters several times, we just saved them here once. So the first one gives you the local world size, so that is the number of GPUs we have per node. The get world size gives you the global world size, how many GPUs we have in total per run. G rank is similar to the Horowitz rank I showed you earlier, and local rank is a unique identifier to identify your GPU devices on a local level. And again, we need to pin the GPUs on your local level to this device parameter. To make sure that each GPU is assigned on one rank. Then as a next step, again, we get our data set, we define our train sampler, and instead of Horowitz size and Horowitz rank, we're just using the defined parameters from the previous slide. So the world size and the global rank as a unique identifier. The batch size, again, is set on a local level here. So the batch size per worker, batch size per GPU. And now we have two interesting options here we can additionally specify. And one is the number of data loading CPU workers. So with that number, you can define how many CPU cores you want to help with the data loading process. And Rakesh will show some evaluation of how to or how this number actually affects the performance later. But we have found that picking roughly a value of 8 on the Eureka machine seems like a good choice. And then you can also set the pin memory to true, which will reserve some memory on the host CPU for transferring data to the GPUs. And this in general helps you to accelerate this transfer process. Then again, we need to define our model and the optimizer. So again, I'm using a ResNet 18, and here we move the model to the GPU with the model.toDevice command. Then we need to distribute the model across the different devices. And then finally, again, define our optimizer. And as in the Horowitz case, in this case, you need to make sure to scale your learning rate with the number of GPUs to get a good baseline performance when compared to training on a single worker. This is again the training function. So things look pretty similar to the Horowitz case. We first need to move our data and from the data we get from the train loader to the GPU. Then we run our training procedure where we send the data for the model, calculate the loss, and do one optimizer step. The all reduce function, you need to collect the results from all GPUs, is a bit different here. And what I show you here is actually a simplified version of it. So here we need to specify which operation we want to do with all reduce. And I chose the sum operation, so that sums up the results from all workers, which of course, to get the average, we would then again need to divide by the world size. And then we just want to print out the results on the main worker. So we need this if statement to just print out things on the GPU with rank 0. And the thing you need to remember when using PyTorch, which is also different to Horovod, is to destroy your process group once you are done with your training. Submitting a PyTorch job on Eureka is a bit different from the Horovod case, and I just highlight the differences here. So because the way we structure this, actually the number of tasks you need to set for PyTorch GDP to run is 1, even though we have 4 GPUs on Eureka. So n task per node needs to be 1. Then again, you need to load the modules, which as PyTorch is installed on Eureka, is pretty straightforward. And then in the end, we need to run this big command to launch our distributed training. So you see that we're using the torch run command, and here again we need to specify the number of nodes and the number of processes per node. So we set actually at this point is where we set those number to 4. And then we need some InfiniBand related configuration so that things run on our InfiniBand communication framework, which we have installed on the Eureka machine. I would say probably it's best to not try to mess with these things, as we have found they work quite well. So usually we just copy and paste this and then insert the name of the Python file, and that's basically it. I don't show you how to do it on Deep here because at least from the last time I've tried, things are pretty similar. But if you're interested in that, you can also take a look in the GitLab repository again, where we have PyTorch DDP example script for running things on Deep as well. Okay, the last framework is DeepSpeed. And DeepSpeed builds a lot of its distributed stuff on top of PyTorch DDP. So we, again, for the initialization, we import the distributed backend of PyTorch, but then also DeepSpeed. Again, we do the initialization where we need to define the backend, which is, again, the NVIDIA communications library. And again, we assign the ranks here, as we did in the PyTorch DDP case, which we actually need for defining the data loaders. Then we again set the data, we again get the data set we want to run our training on, and we define the data loaders actually in the same way as we already did in PyTorch DDP. Then we build our model, again, a ResNet 18. And this is where things start to be different from the PyTorch DDP case, because here we initialize our model and also our optimizer in a distributed fashion by calling this deepspeed.initialize function. And this function actually relies on a separate JSON file to get the information, for example, for the optimizer. As you see, I don't have an optimizer specified here. Instead, I do it in this separate JSON file. And here you can set the type of optimizer you want to use and the learning rate again. Again, keep in mind to scale it with the number of workers. You can already, just from this JSON script, enable half precision, which will usually speed up your training process. And probably the most interesting thing when using DeepSpeed are these zero optimizations, which can choose different levels of optimization you want to use. And yeah, for more information, just check out the DeepSpeed website where they show you what each level of optimization, what kind of methods stands behind it. I want to mention that probably most of them are also more interesting once you're using model parallelism and not for the data parallelism case. Training the model, again, looks pretty similar to the PyTorch case, but instead of doing this device declaration the way we did it earlier, we do the device handling in DeepSpeed with this model.localRank. Then we run our basic trading procedure. And for averaging the results, we again rely on the PyTorch DDP backend with the same or reduce commands. The Slurm script on Eureka, for example, again, looks a bit different. General configuration and modules are all pretty similar, but when you look at the commands, you need to write to run the Python script, so the last part of your Slurm script. In this case, we use the DeepSpeed launcher. And for this DeepSpeed launcher, we specify, again, certain things like node rank, master address or master port. And then it also wants a list of nodes, which actually how to create this list of nodes I didn't include here because it's not so interesting. But again, if you're interested in that part, just take a look at the GitLab repository. Yeah, and then you put in the name of your Python file. You pass the JSON configuration file that contains the information of the optimizer, and then you should be good to go to train your models with DeepSpeed. I will now want to give a small introduction how to actually submit a job on the cluster, and I have something pre-recorded for it. Okay, I think you can all see that. It's running. Okay, so the first thing you do that once you have, for example, logged in to a machine is to do this module eval command, and with that you can take a look at all the modules that are available on the system, and by that, for example, find out if a certain library is already installed. Now you see, for example, I have found that there's PyTorch, and I want to know how to load that module. Then I can do module spider and yeah, say the name of the library. Then it shows me what kind of different modules, what kind of different PyTorch libraries are already installed on the machine. And now if I'm interested into knowing how to load a specific library, I do module spider with the specific name of that library. And then it will show me here which libraries I need to load before I can load this PyTorch module. Okay, so that was just to show you how you can find out specific information about the pre-installed libraries. Now you see I have already prepared the Python file and the bash script this is a look at the Python file, basically the same thing I showed you earlier. So I'm demonstrating this for PyTorch DDP. And when you take a look at the bash script, it's also, the fix I showed you earlier. So now we are doing a small scaling test. So first I set the number of nodes I want to run this on to 2. So we specify we want to use 2 nodes. Then we use the sbatch command to submit the job. And then with the sq minus u and plus your user identification, I can check the current status of my job. And configuring means that the job is configuring, loading the module, starting up, still configuring after 13 seconds. And now you see that the status is running. So that means that my job is running and the computations are taking place. As I said, I want to show you a small scaling test. So now we change the number of nodes to 4, so twice the amount. Save the whole thing, and with sbatch again submit a job. And now as I do the sq command, I can see that both of my jobs are already starting. One is configuring and the other one is already running. Now at different points in time, you can of course rerun the sq command to see the current status. I will forward this now. So you see, takes some time. Once it shows this CG status, that means it's coming to an end. And now you see that both output files for the 2-node case and the 4-node case are there. Let's first take a look at the 2-node case. We see a runtime of roughly 73 seconds. So that was how long it took to calculate 10 epochs, I think. And now we take a look at the output file for the 4-node case. And here we see that it just took 50 seconds. So far from perfect scaling, because I probably didn't use any optimization, and also because, of course, the Cypher dataset is pretty small. So distributing it across 4 nodes, which would already be 16 GPUs, is not that much. But still, you see there's some speed up you can achieve here. And that's it by me. And now Rakesh will continue with an application of PyTorch DDP in one of our RAISE use cases.
I think I'm muted. Okay, you can hear me, right?
Yes.
Yeah. Okay. Just turn on my laser pointer. Okay, yeah. So thanks everybody for joining. So as Marcel said, I would be showing now the application of the things Marcel showed in a specific use case. So this is task 3.1 within work package 3 in the CoE RAISE project. And this is related to turbulent boundary layers. So basically, I'm going to give a brief introduction into this use case, and then go through a skeleton of the script that we have. So I'm going to talk more along the lines of the use case. So looking at the data loaders and then and the input configuration that we wanted to have in order to change the parameters and see how we can improve the performance of the model. And then we also worked in doing some optimizations to improve the performance of the model. So basically, I'm going to share some of the improvements that we were able to make, and give you some recommendations on how you can adopt them as well. So to introduce the use case itself, I won't go into the details, but basically what we have on the left here is the computational domain. So we have a flat plate over which there is an airflow. So on the left here is the inflow, and then we want to look at the development of the turbulent boundary layer here. And specifically, we are looking at reducing the drag over this flat plate. And in order to do that, we are introducing these transversal surface waves that you can see. And this is one of the active drag reduction technique. Using this, and by introduction of the surface waves, we are able to reduce the drag, which of course leads to more efficient flying. So in this case, we have two parameters. Of course, introduction of this traveling surface waves involves some power. So we are also looking at net power that is used here. So basically, these are the two parameters, CD and PNet, which we want to predict. And in order to introduce this actuation, we have a few parameters. This is the equation which defines these surface waves. So basically, we have, for example, the amplitude, the wavelength, the period, and we want to find the dependence of these parameters on this actuation, on the actuation parameters that we have. So this project is in collaboration with RWTH Aachen University, and so we have a data set which is from an LES solver, which is a high fidelity solver. Of course, it's very expensive. So we want to use machine learning to speed up this process somehow. And the aim of the machine learning investigation would be to use somehow these actuation parameters, and from the network predict the drag and the net power in the end. So I don't go into much details of this network. Here we already have a public deliverable which has been published already with respect to this use case. So if you want to know more about the specific fluid mechanics aspects, please have a look at this deliverable. So to talk about the data set, so this is the computational box that I was showing just now. So basically, the data is filtered, and this part shown by the red box is taken out, and that is the data that we have, which is roughly 8.3 terabytes. So of course, as you can see, that's a very large data size, and it's also maybe important to specify here that this data has already been published, and it's openly available on the RAISE website. So if you would like to play around with it, you are free to have a look there. Just to give you introduction to what is contained in this data file. So basically, we have HDF5 files, and we have 3 velocity components, U, V, W, and the density and the pressure fields. So from the data loading point of view, what was required to handle is this non-uniform data size. So basically, as I said, we have different actuation parameters, and this and because of this different actuation parameters, we have these different sizes of these computational boxes. So the input to the or to the neural network basically is non-uniform, and so we needed a custom data loader which takes into account these non-uniform domains. And so as of now, we have an autoencoder network which is coupled to a drag and net power saving prediction network. I won't go into the details of the network itself, but I will show you now a few input parameters and configurations that that we have implemented in the open source Git repository that we have now. So as I said, we have custom data loader. So this is quite generic, except a few things which I would like to point out here. So basically, params here is the variable which are the actuation parameters that we have from the computational box that we are reading. So that is an input to the network which we have. Then we have the targets. So basically the drag and the net power saving, which you want the network to predict. And so these are of course the targets. And then we have this uniform data function, which basically takes care of making all these computational boxes uniform. I don't show the details of this function itself, but if you are more interested, please get in touch with us. Everything is available in the repository. Then looking at a few input arguments which are essential. These are very generic for any machine learning program. For example, the batch size, the number of epochs, the learning rate, for example. Then, for example, the weight decay, which is required in the which can be useful for having a good optimization. Yeah, for example, shuffle, schedule. I won't go into the details here, but basically these are the things which you would want in your input file, such that this can be modified easily from the start script. And then a few configurations which are useful for the distributed learning setup that we have. So first of all is this number of workers, which Marcel was talking about. So basically here we have the number of CPU threads that we want to have, which help us in the data loading process. Then there is the prefetch factor, which loads a certain amount of data beforehand, such that there is no lag in between two batches. And then, of course, the backend, which also Marcel was talking about. So in this case, in our case, the default is this NVIDIA communication backend, which we use. But there are also other options which are available within PyTorch. So if you are interested in knowing what kind of difference it makes, so basically there is this table which is available on the Torch website, which shows like which kind of operations are possible and corresponding to what backend. So basically in Torch there is glue, MPI, and nickel, and basically if you use nickel and a GPU based processor, then you have most of the operations are possible. Then looking at a few other functions, which also Marcel was talking about, basically this all reduce function, which is required to reduce, for example, synchronize the gradients across different processes or workers. And basically in this function, you can specify what kind of operation you want to do. So on the top here, we do a sum, for example, and on the bottom, we do a max of a certain field across these different workers. Then there are other such implementations that we have in the repository. Just to point out for example, this all getter, which we use, for example, to gather the losses in a to a specific list, and then we compare this at some point. So I will be showing the application of this basically for creating checkpoints. So this is something which is very useful for this is actually very primary, and you would always need it when you are doing this, when you are doing a machine learning workflow. So in distributed, so I'm going to show how we do this in our case. So basically we use a counter here, which is given by this variable best accuracy, and then we check if this best accuracy is if the current loss is lower than the previous best loss that was reported, and if that is returned as true, then we call this save state function, which basically is shown here. So what we do is we use this par altogether object to this particular function to find if there has been a better configuration or better run across any worker, and if this is returned as true, we save that particular state. And so that's the function, and then within the script itself, we have this implementation. I won't go into the details here, but if you have any doubts, please get back to us. This is in the repository as well. So regarding the network itself, so in this particular case, we have as I said, an autoencoder which does drag and net power saving prediction. So basically, there are two different networks here. On the top is the encoder and the decoder, which are part of the autoencoder network. And then we have some fully connected network, which gives this drag and net power saving. Find the network in the end outputs these two parameters. I don't go into the details here because that is not the purpose of this particular talk. But if you are interested in more details about the autoencoder itself, we already have had a presentation last year, and this is available on the YouTube channel if you would like to see that. Okay, so this was about the skeleton of the network that we have in the repository. The next part is on the optimization. So basically, we have this implementation, but we wanted to see if we could improve the performance of the code itself. And here in this part, I would like to share some of the experiences that we had during this process, and maybe those are things which you would also want to consider when you have your own implementation. So what we did here is basically looked at the PyTorch profiler, which gives us the share of computational time per process. So basically what we observed here is that the data loading component, which is the one which is the most computationally expensive, which is expected, and especially with the kind of data size that we have in this case. And where are the improvements we can do? So basically, this could be in two different aspects. So first is on the data loader itself, which becomes critical for large data sets as we have, and also non-uniform data sets which require more number of operations, since you need to do certain reshaping functions. So there are different libraries. For example, there is NVIDIA-based DALI library. Then we also looked into multi-threading, as we saw, like with this number of workers argument in our input configuration file. Then with this preload algorithms, for example, with this prefetch factor. Then we also looked into a mixed precision. So basically having a lower floating point precision for the parameters of the network. Then looking at, for example, pin memory, which also helps to fasten up the process. Then for larger networks itself, there are different ways to do it. So for us, we have tried the CUDNN algorithms, which are NVIDIA-based tailored algorithms, which are also useful for achieving better performance. Then looking at warm-up, for example, starting with the lower learning rate during start of the training. Then model parallelism is something which we have not yet done, but it is something we would like to explore. Specifically at this point, our models are not big, but we are also going to explore this at some point, and then looking at network mixed precision, as I already mentioned. So how this looks like, so this is something which Marcel talked about at the point where he said the number of workers is set to 8. So in this particular slide, what we did is use PyTorch DDP. Then we had a smaller version of the turbulent boundary layer dataset, which is 22 gigabytes. Set few operating training parameters, and then we looked at the speed up for different by varying the number of GPUs and the number of threads. So what we observe is if we keep so in this case the data set is very small, so it does not really help by increasing the number of GPUs here. But if we have larger data sets, what we observe is that after a certain point, the increasing the number of threads does not really help. The behavior is quite unstable. So in our case, we observed that number is somewhere around at 8. But this is something which should, of course, be tested for each individual case, and I would really encourage you to do some test of this sort, which helps you to figure out this number. But it really helps us to achieve significant speed up compared to not using any CPU workers for the data loading phase. So let's look at a few results by doing these optimizations that I was talking about. So we gathered all the optimizations and looked at what really works for us, and this is the best available performance that we could get. So this is again with the PyTorch DDP package, looking at the larger data set here. So basically with this 8.3 terabytes data set, with a small number of epochs, because here we just want to look at the parallel performance, then a few other parameters that we set here. So in this case, basically, so the red line is one where we don't have any optimization, and the blue line is with most optimized for the optimized case. And as you can see, we have been able to reduce the training time from 25,000 seconds to around 3,400 seconds per epoch. And the corresponding speed up and efficiency have been also satisfactory for us. So basically the take home message here is that this kind of optimizations can be very beneficial to improve the performance of the network. So to sum up, so basically we have a AI framework which has been tested for multiple prototypes. So basically with Deep here, and also with the BSc AMD machines at the Barcelona Supercomputing Center, and with production systems, for example, with Eureka and Jules. So we have tested this AI framework for these different systems, and the open source code is actually already available. So basically, if you go to this link, you can already download the open source version, which is not as detailed as the private version that we have, but we are trying to continuously update that. And there is already an implementation of the turbulent boundary layer problem that I was presenting. Then also, yeah, as we saw, the code optimizations work, and this is also something which might be useful for other use cases and other applications. Other than that, there is also a lot of documentation available, at least so for the JSC machines. There are links which look something like this. So for example, here I post a link for the Eureka machine, but yeah, there are other documentation available as well. So please have a look at that. Okay, so with that, I am towards the end of my talk, and I would be happy to answer questions.
All right. Yeah. Thank you very much, Rakesh. Thank you very much, Marcel, also for the previous talk. And then, Rakesh, I think you also shed interesting lights on how really people can use it. But let's now open also the questions area. We had already a very nice chat history for those that didn't check it. So there's already some interesting, nice discussions around do we just support Slurm as a resource management system? And so on. So I think these are things we should look into as well, of course, but we may focus first on the race partners as we determined to do, but then of course also maybe working with the EuroHPC JU hosting sites, which really have, then some word to say what are the resource management systems they would like to deploy and use. But without me much talking, are there any more questions from the audience maybe?
Maybe I can just also address the question by Kurt.
Sure, go ahead.
So yeah, with this nickel thing. So as I showed in the beginning, when you initialize your distributed backend, you have to specify which backend you use. Yeah, which when you set to nickel, I would expect to use the nickel or reduce. And so I've also run some compiling. Some profiling, okay, it's not very nice to show here, but yeah, when you run profiling on your PyTorch code, you can, for example, see these nickel or reduce functions here. So I do expect that that once you specify the nickel backend, then it will also use these nickel or reduce function. And the second thing, how to make sure you're actually using the number of GPUs you specify. First, you can, of course, print out your global rank or your world size. And if that doesn't match the number of GPUs, you can see that there's a problem. In terms of live monitoring, there is this, where did I put it? So-called LL view. Sorry, give me just a second. Here it is. So LL view is a backend a tool which helps you, which gives you actually like this part of the information you're interested in. I think it's currently only available on Eureka or Jubels, not on Deep, unfortunately. But here you can see for each job, for example, your GPU utilization in a live fashion. So yeah, you see here I only have roughly 30% GPU utilization, but across every GPU. So if you see there's like some GPU has 0% utilization, that usually means that there's something wrong. But Morris, do you know if we have something similar on Deep?
I think largely LLView gets this information from the resource management system itself. So it must be a way how you get it actually from the resource schedulers. That's how Wolfgang usually implements the LLView.
Okay.
Of course, it's very unique in the moment based, but I think there are ways to find out. There's actually also some NVIDIA tools I think that can help there. But yeah, it's an interesting question. But yeah, I think you addressed it, Marcel. Maybe another question. Still some time. Okay. Yeah, we had lots of questions already in the chat. And of course, for everyone who is not directly involved in RAISE, we are also open-minded to get input from different sides. So if you think there's a component missing from another CoE or so that you're using it, interestingly enough, in many use cases, and we didn't have this component on the radar, that would be also good to hear from you. Otherwise, I think if there are no big questions, we should maybe not do it much longer as needed. My last call for questions now, maybe once, twice. Okay, if that's not the case, then I would just maybe share some closing slides, and then we can already give you a sneak preview what we have in the next training. So thanks again for joining, and also thanks for the speakers here, Marcel and Rakesh again. That really shows you insight how we want to use these components of the framework. If you want to know more and stay active, basically observing this and monitoring our progress, we're just midway basically, so we have still more interesting months to come with real results to deliver. So then follow us on the RAISE website. Today was really thinking about the unique AI framework, and obviously this was just one part of it, where we talked about the complexity of the different modules, how use cases can adopt it. Further trainings will be also on the automation that we have, this kind of idea of a maybe, let's say, job script generator that helps you a little bit with modules in that area, so a bit more semi-automation if you want, and other ideas with Jupyter kernels and so forth. So of course, this AI framework has many facets on many different areas, and today was really just, let's say, small first impact on what we have already there. I think Rakesh nicely pointed out today that there is already a GitLab part. So basically in his presentation at the end, you have seen there's already something accessible for the community. So if you're interested, please have a look in this. We're also very open for feedback. And of course, the idea is now in the second part of RAISE to extend this. So we will improve on the GitLab, will provide more and more out with documentation, how to really make use of this software framework components. And then, of course, the YouTube channel is for you a big source of information. If you want to know more, we have monthly trainings. We stopped in the summer a little bit, but if you please go to YouTube and want to learn, more information, what we basically do in the CoE RAISE project is large, and also want to know a little bit about maybe different AI methods, follow us on YouTube, and there will be also this seminar that you have seen today, obviously coming very soon on YouTube again for you available. But also make sure to follow the links that have been inside the presentations. I think once again, Rakesh pointed already to our first GitLab, which is very important so that we get early feedback from the community back who would like to adopt certain components. We have also seen in the discussions, of course, we have to get new requirements in. The question was, is Slurm really the only job script that we want to support, or are there maybe others like PBS, Torque, and so on? But there's also a certain saying, I would say, that firstly, Slurm may be broadly adopted, and secondly, the porting from one to the other might be not that problematic, because in the end, many of these aspects are also partly in Python. And in the end, many of these were the right modules at the right time, which is, let's say, independent from the resource management system a little bit. So here and there, I think we are getting there. We may not support everything, but at least we can help many researchers with this framework, as you have seen, with lots of time-wasting activities that they should do otherwise, of finding the right modules, the right scripts, and the right combinations of those. Just as a sneak preview for next time, if you have time in September, the date and time will be announced, but as you know, it will be mostly at the end of September. There will be a training on so-called transformer models, which are quite interesting models that got quite some, let's say, momentum in the AI community, and also within RAISE are more further discussed right now. This includes different elements, so we will have a short introduction, of course, to the general transformer ideas, and then also include several facets which are very similar, like multi-scale vision transformers, video vision transformers, or so-called shifted window transformers. So stay tuned and join us in September if you want. With this, I would like to thank again everybody for joining, and we close this webinar. Thank you very much, and see you next time.
Yeah, thank you. Bye.
Thank you.
Bye.
Thank you.
Goodbye.
Bye.